In this video, we are going to see about virtual memory. Virtual memory is the separation of user's logical memory from the physical memory. Only part of the program needs to be there in memory for execution. Logical address space is much larger when compared to your physical address space. So this allows the address spaces to be shared among several processes, and it is more efficient in process creation. So many programs can run concurrently, so it needs less IO when it comes to load or swap the process. So this virtual memory is a technique that allows the execution of processes that are not completely there in memory. So the main advantage of your virtual memory is that the programs can be larger than the physical memory, so the programmers are free from the concern of memory storage limitations. So this virtual memory allows the process to share files easily and to implement the shared memory. So this diagram shows the virtual memory is larger than the physical memory. So here if you see, this is your virtual memory or the logical memory, and this is the memory map unit, and this is your physical memory. So as we know about physical memory is the set of frames. So this is your backing store from where you will be taking the pages, and we will be moving it to the physical memory when needed. So when we move those pages, we will be seeing whether we have a free frame. If we have a free frame, we will move that pages to that particular frame. If there are no more free frames available, what we will do, we'll be using some page replacement algorithm and swap out the page and swap in the required page inside. That is the structure of your physical memory. So what is your memory map unit is going to do? This memory map unit will be acting as an intermediate between your virtual memory and the physical memory. Okay, this virtual memory is communicating to the physical memory via your memory map unit. So next one which we need to know is the virtual address space. So this virtual address space is the logical view of how the process is stored in memory. So usually it starts from the address 0, and it is a continuous addressing until the end of the space. So as I have told you, physical memory will be the set of frames, and your memory map unit is going to map your logical memory to the physical memory. So the virtual memory can be implemented via demand paging or demand segmentation. So this is the virtual address space, and here if you see, you have shared libraries in your virtual memory. So it is using some shared pages. The shared pages will be common to all the process. All the process can able to access this shared pages. So this is the concept of your shared library in your virtual memory. So the next concept which we are going to see is demand paging. So demand paging, it will bring the page into memory only when it is needed. So because it is doing like this, the main advantage of your demand paging is that it needs less IO, and it needs less memory, and it has a faster response time, and then more users can use it. So you if the page is needed, okay, if the page is needed, what you will do, you will be having something called as page table that we will be seeing it after this. So in the page table we will be having frames, okay, the frame numbers and the valid and invalid bit will be having that. So when the page is needed, you will go and see in that page table whether the page is already there in memory. If it is there in memory, you will be referencing to it. Okay, if it is an invalid reference, then you will abort it. Okay, if it is not there in memory, so you have to bring it to memory. Okay, from your secondary store you have to bring it to memory. Okay, so that's what your this thing, the page table, is doing. Okay, next one is lazy swapper. So this lazy swapper, what it does is it never swaps a page into the memory unless the page will be needed. So the swapper that deals with the pages is called the pager. So what this will do is, before swapping out a particular page, this pager will guess whether this page will be needed in the future. If it is needed in the future, it won't swap out the page, and it will swap out the page which will not be needed in the future and brings in the desired page. Okay, so if the page that is needed is already there in memory, means it is called as memory resident. Okay, and then if the pages are not there in memory, so it has to bring that page into the memory. So it needs to detect and load that page into the memory from the storage. Okay, so it, without changing the program behavior and without the programmer needing to change the code. Okay, so this is what I talked about, right? So this is the main structure of your page table. So here if you see, you have the frame number and you have valid and invalid bit. So this is the structure of your page table. Initially all the entries of your valid and invalid bit will be I. Okay, so all the entries of your valid and invalid bit initially will be I. Okay, so when a page is allocated to a particular frame, it will be changed to V. Okay, that means that the page is there in memory, it is memory resident right now, so it will change that valid invalid bit to V. Okay, that's how your page table works. And next one is page fault. So what does mean by page fault? If the page is not there in memory, you have to take the page from the backing store and you have to put it there into the memory. So if the page is not there in memory, then it is called as the page fault. Okay, so I need to bring it to memory. Okay, so just what you will do, I will take that frame and I'm going sorry, I will take that page, I will bring it to the memory. So before bring it to the memory, I will see whether I have some free frames. If I have the free frame, I will take that page and put it there in my free frame. Okay, and then once I put that page into that frame, what I need to do in my page table, I need to convert my valid and invalid bit to V. Okay, so this is called as your page fault. Okay, if the page is not there in your memory and you are taking that page from your storage space and you are putting it into the memory, then it is called as the page fault. Okay, so these are the steps in handling a page fault. So first one, it is loading M. Okay, load M, I am giving the instruction called load M. So this is going and seeing in my page table whether the entry is there. Here the entry is not there because your valid and invalid bit is as I. Okay, that means it is invalid, so it is not there in the page table. And then it is sending a trap signal to the operating system. This operating system meanwhile it sends a signal to the backing store and to see whether that page is available in the backing store. If that page is available there in the backing store, it is bringing that missing page to the physical memory. So when it brings that page to the physical memory, it will see whether any free frames are available. So it checks and finds out the free frame and put that page into that frame, and then it goes and resets the page table. Now this entry will be your bit invalid and valid bit entry will be changed to V, and then it restarts the instruction and loads that particular value. Okay, so this is the particular steps in handling the page fault. So the next one is aspects of demand paging. So in extreme case, it starts the process with no pages in memory. Then it is called as pure demand paging. Okay, if it starts a process with no pages in memory, then it is called as pure demand paging. Okay, so these are the performance of demand paging. Okay, and next one is copy on write. So this copy on write, it allows both the parent and child process to initially share the same pages in memory. So if either process modifies the shared page, only then is the page copied. Okay, this one it is more efficient in process creation as only modified pages are copied. So here we need to have a free pages that are allocated to the pool of zero fill on demand pages. So you'll be having a pool. In that pool you have the free frames for fast demand page execution. So here if you see, you have a variation between a vfork and the fork system call. So here in case of the vfork, the parent will be suspended until the child finish off with its copy on write operation. Until then, the parent will be in a suspended state. Once the child finish off with the copy on write work, then only the parent can resume its work. So that's what the difference between your vfork and fork. So this is what copy on write is all about. So these are the basics of your virtual memory. So if you have any doubts, just comment on it. Thank you.